The normal distribution is the famous bell curve. So there's many random variables, IQ scores, test scores, height distributions that occur in the world that have a probability distribution that is in this classic shape. It's a symmetric distribution, it's centered at its mean, and then there's these following rules of thumb that are handy to know. About 68% of the values lie within one standard deviation of the mean. So we have a bell curve here. It's centered at its mean. Choose M for mean. If we go one standard deviation smaller than the mean and one standard deviation larger than the mean, if you have a value somewhere in this range of values, there's a 68% chance that you're within one standard deviation of the mean. 95% of the data is within two standard deviations of the mean. So if we have a mean here, we can go down two standard deviations, up one standard deviation larger than the mean. 95% of the data lie within this interval of values, within two standard deviations of the mean. So we're using the curve here, the little graph, to help physically represent what percent of the data is going to lie within an interval on this number line. And then virtually 100%, 99.7% of the values are going to lie within three standard deviations of the mean. So say you took a test, and you're told after the test that your test score was more than two standard deviations greater than the mean. That would mean you had a test score, you're one of the people in this small area. So you have a very good test score. You've done better than almost everyone in the class. If, however, you take a test and you're more than three standard deviations below the mean, you are way down here. Let's hope that doesn't happen. Okay, so the shape of the curves is determined by its mean and standard deviation. The larger the standard deviation is, the more spread out the bell curve will be, but the total area under the curve will be 1 or 100%, whichever way you like to think about it, no matter what the standard deviation is. The curve is going to be symmetric about its mean. The vertical line cuts the distribution in half, so the probability of being less than the mean is going to be 0.5, and the probability of being greater than the mean is going to be 0.5. The normal distribution is also what's called a continuous distribution. So the probability of a value being exactly equal to a number is 0. Instead, what we do is calculate the probability being within an interval of numbers. So rather than calculating the probability that a random person has a height of 64 inches, instead we'd be calculating the probability that a person has a height between 63 and 65 inches. So in general, when we're working with the normal distribution, we don't find the probability of x being exactly equal to a number. We find the probability x is between a number, less than a number, greater than a number. And again, we'll be drawing sketches to help us keep track. So the probability that a random variable has a value in an interval is given by the area under the curve. Let's make a bell curve here. So the probability of being somewhere between two values on a number line is going to be represented by the area under the curve that is above that number line between those two values. Okay, so using our rules of thumbs, let's play around with this a little bit and see if that helps make it a little more clear. Say there's a test given to a large number of people. We're told that it's normally distributed, so it's got that bell-shaped curve centered around a mean of 80, and that there was a standard deviation on the test scores of 5. So standard deviation is a measure of how spread out. 5 is a fairly small standard deviation, so most of the test scores are clustered close to the score of 80. Now, because the mean is 80, and it's normally distributed. The probability test score is less than 80, so this distribution is centered at 80. The probability of having a test score less than 80 is represented by the area under the curve on that interval, and because the total area under the curve is 1, 80 splits the data in half, so 50% of the data is on this side, and 50% of the data is on this side. So the probability test score is less than 80 is going to be 0.5, or 50% if you prefer that. The probability that a test score is between 75 and 85, again, we know this distribution is centered on a mean of 80, and we know the standard deviation is 5. I'm using sigma here to represent standard deviation. And I'm interested in the test score being between 75 and 85. So I'm interested in the probability of the test score being in this interval between 75 and 85. So that includes 76, 77, all the way up through 85, being in this interval somewhere on this number line. I can represent that area here. Now here's where I carefully have some big numbers here. The standard deviation is 5, so 85 is 1 standard deviation larger than the mean. 75 is 5 points below 80, so it's 1 standard deviation below the mean. So being in this interval 75 to 85 is the same thing as being within 1 standard deviation of the mean, and 1 standard deviation of the mean, we know from our rules of thumbs, means that there's a 68% chance of being in that interval, or 0.68. Okay, same idea. Probability test scores between 70 and 90. So again, 80's here in the middle. 80, 85, 90. 80, 75, and 70. So again, our standard deviation is 5. So 90 is 2 5-point steps above 80. So 90 is 2 standard deviations above 80. And 70 is 10 points below 80, which is 2 standard deviations, 2 units of 5 below 80. So if I'm interested in the probability of test scores between 70 and 90, means somewhere along this interval on the number line, that probability is represented by the area under the curve between the 70 and 90 line. And going by my rules of thumb, I know 95% of the values lie within 2 standard deviations of the mean, and 70 and 90 are within 2 standard deviations of the mean, so this probability is 95%. So there's a 95% chance that a test score is going to be between 70 and 90 on this particular test. And then one last one here. I have to kind of do some mental gymnastics. The probability that a test score is greater than 90. So again, the mean is 80, and 90 would be about here. And I want the probability of this test score being greater than 90, means somewhere out here. So now I already know that 90 is 2 standard deviations higher than the mean, and I know that 95% of the data lies within 2 standard deviations of the mean. The total area under the curve is 1. And 1 subtract the 95% is 5%. So this area is 95%. I've got 5% left to split between this tail and this tail. So this area is half of 5%, and this area is half of 5%. So this part of the area, of the total area under the curve, which is 1, is half of 5%. So 0.025 or 2.5% is probability of a test score being greater than 90. Okay, so a little background again. Pretty much every set of data that's normally distributed will have a unique mean and standard deviation. So we were looking at an example that had a mean of 80 and a standard deviation of 5. There are other distributions that have a mean of 81 and a standard deviation of 4. There's an infinite number of possibilities here. But for now, we're just going to focus on what's called the standard normal distribution. And a standard normal distribution has a mean of 0 and a standard deviation of 1. Very few applications are going to have that mean of 0 and standard deviation of 1, but we're going to focus on that for now, get the handle of the mechanics of working with the normal distribution, and then we'll learn how we can adapt any distribution to work with the same rules. Okay, so standard normal distribution, mean 0, standard deviation of 1. We're going to use a table. You should have a copy of it there with you. It's going to give the approximate probabilities of values for a variable being within a standard normal day. Sorry. It's going to give us the probability of being less than a particular value. So if you look at your table, you'll have a Z column that has various values that represent standard deviations. The table is always going to give us a probability being less than a particular value. And what we want to be sure to do is go ahead and do the sketches and look at the areas under the curve, because it's going to help us keep track of what we're doing. Again, it's going to seem a little odd at first. Once you get the hang of it, it's not hard at all. And then we're going to use this to get into some more applicable uses of it. Okay, so start off with one here. Using our standard normal table, if we have a standard normal distribution, mean of 0, standard deviation of 1, if we look in our table, go down the column, it's your, well, clear on the right edge, we're going to look for where the Z value is 2.15, and right next to that is the probability of being less than 2.15. So standard normal distribution has a mean at 0, and we're going up a little bit more than 2 standard deviations. We're going to where Z is 2.15. We want the probability of Z being less than 2.15, and that's represented by this area under the curve. That value's been calculated for us, and that area there under the curve, which is the same thing as the probability, is 0.98422. 5 decimal places of accuracy. Pretty good. Okay, that wasn't too hard, right? So when we're on the standard normal table, we can look up a particular Z value. The probability next to it is always the probability of being less than that particular Z value. So there's a 98.4% chance of getting a Z value of less than 2.15. If we look at the Z of 0, we can see the probability is 0.5, and that should make sense, because if we have a Z value of 0, the probability of being less than 0 should be 50%, because that's half the area under the curve. Let's do a few more of these. Just want to change pages. There it goes. Okay, so this one, I've turned the inequality around. This time I want the probability of Z being greater than negative 1.75. So think of this as a number line. Zero's here in the middle, negative numbers to the left, positive numbers to the right. So negative 1.75, well, around there. And then when I go to my table and look for where Z is negative 1.75, the probability is very small. So again, we're always given the probability being less than the particular Z score. So this area here is quite small, 0.04006. Now I'm actually interested in 0.175 being less than z or z being greater than negative 1.75. I want the probability being somewhere here on the number line, which is going to be all of this area here. Now remember, the total area under the curve is 1, so to get the area I actually want, I need to take 1 and subtract the 0.04006, and that gives me 0.95994, and that's the probability, or 95.99% chance, that a z-score is greater than negative 1.75. So you can see how using the graph helps us keep straight any mental gymnastics we need to do to adapt what we're given in the table to what it is we actually want. Technically, drawing the graphs isn't required, but I know I always make mistakes if I don't do it. Okay, so here we got the probability being on a defined interval. Again, 0 in the middle, negative 1.5 would be around here. These don't have to be exact, but just help us keep track. 2.5 probably be around here. And we want the probability of being in between these two values, and that's going to be represented by this area. So just guessing, I'd expect a fairly large number, something close to 1 here. As I look up each of these two values, let's see here, a piece of the table, negative 1.55. The probability being less than that is 0.06057. So that's this area here. And then when I look up the 2.5, let's see, there we go. I've got 0.99379. And that's all of this area. So I've drawn an extra graph here. When I look up the 2.5, the value I'm given, the 0.99379, is the probability being down here. Then when I look up the negative 1.55, that's this area here, 0.06057. So I've got this area, I've got this area, and what I want is the area in between. So what I can do is take the 0.99379, all of this area, on over, and then subtract out this area that I don't want, the 0.06057, and do that subtraction. Get my final probability, 0.933. I think I left something off there. 1, 2. So about a 93% chance of being within this interval. And again, this sketch is going to be helpful to keep track, and you might find doing a couple of sketches is what makes things clear to you. Okay, this one's just a little different looking because I want the probability of z being between two positive values. The mechanics are the same. It's just kind of a squeeze to get much of a sketch in here. So 0.45, that's a little bit smaller than half a deviation, so that's quite close to the 0. 1.75. And again, here the graph just gives me a visual representation that I would expect a pretty small number here for my final probability. If I get a probability of 98%, I know I've messed something up. So again, I've got two different values to look up on my table. The 0.45 on my table gives me 0.67364. And that's this area here. It's a little bit over 50% because it's just a little bit right of the mean. And then the 1.75 is right there. And that gives me a probability of about 96%, 0.95994. And again, I want the area in between, so I'm going to subtract these two numbers. So I'm getting about 28%, 28.6% chance of being in this very short interval, and physically that's represented by this area under the curve. Okay, probability of z being greater than 1.8. 1.8, positive value, so it's right of the zero. And I want the probability of z being greater than that, so again I want the area in the tail this time. When I look up the 1.80, it's going to give me this area. Let's see, 1.80, 0.96407. Is the area I don't want. The total area under the curve is 1, so I'll take 1, subtract 0.96407. And my probability of being greater than 1.8 is 0.03593. About a 3.6% chance of being greater than 1.8 standard deviations above the mean. Okay, more here. This was a little bit backwards. So instead of finding the probability of z being greater than a value or less than a value, this time I'm going to give you the probability, and we're going to try to find the cutoff value. So I want to find what value of z should be used if we want the probability of z being smaller than that value to be about a third. So again, we know the 0 splits the graph in half. So there's a 50% chance of being smaller than 0, a 50% chance of being greater than 0. And I want some value so that probability of z being less than that is about a third. So instead of splitting the data in half, I want to split it so that this area is about 1/3, which would mean this area would need to be about 2/3. So about 0.33 and about 0.667. So to do this, I'm going to have to look at my graph, my table of values backwards. Okay. These values are the z's. These are the probability being less than z. So what I'm looking for here is a probability of about 0.33. And I don't actually have that on my chart. It's somewhere in between these two values. So I'm going to have to do some approximating. There is a way to use Excel to find this exactly, or we could do some interpolation between two numbers. I'm just going to go with the closest value. So I want the probability to be about 0.33. And the two values I've got to pick from here are 0.32636 and 0.34458. So 0.33 is a little closer to 0.326 than it is to 0.344. So what I'm going to use then is a z value of negative 0.45. So if I want a value of z so that the value of being less than z is about 1/3, negative 0.45 is going to be my cutoff value then, so that this area is about 1/3, 0.326, and this area will be a little bit more than 2/3.